Okay, so you all turned in your midterms last time, obviously, and we'll have those graded by next week. It shouldn't take too long. So I should have them all done by Tuesday, the latest. So far, from what I saw, everyone did pretty well in the first 2 pages when I skimmed over. So I guess we'll see. Anyways, we'll go ahead and continue to the new material. And also, before I start the new material, I was wanting to gauge everyone's opinion. For the third assessment that we have, I have on the syllabus that it is something that you're going to take on Moodle. Would you rather just take it in person? I mean, it seems like everyone enjoyed, or at least tolerated, the paper version more. I mean, again, if you want to take it online, that's fine, but I was wondering if you want to take it in person, you just take it, you just come to class, you take it in person and all that stuff. So if you'd rather Moodle, I can have a Moodle alternative. But
do you have an idea of when it would be right now?
I'm not too sure.
Okay.
But so I think I'd rather do one or the other, actually. So if there are people, it does seem like there are a few people who would rather Moodle, then Moodle it shall be. But if it is Moodle, it's going to be longer. If it's in class, it'll be a class period. So just keep that in mind. So far, it's still going to be Moodle, but if there was an overwhelming majority for in person, then why not? But that's just something to keep in mind. But if you want it to be in person, let me know. But other than that, I just wanted to put that idea out there just in case. Okay, so let's go ahead and start with the new material. So we've talked about the various trig functions and ways to apply them. And we're going to talk about how to graph them. We haven't really looked at graphs of sine and cosine yet, or the other trig functions, so that's what this chapter is dedicated to. How do you construct these things? And if you say, well, of course, I put it in the calculator, then no, that's not good enough. We're going to talk about how to derive the graph for, well, we'll start off with sine and cosine. And really, the best way to begin this discussion is by considering, well, let's start off with sine. What does sine look like, the graph of sine? And we're going to start off by just plotting some points on the sine function. So let's consider x and sine. And let's just consider a few values. So maybe we'll do some of the special angles. So 0, pi over 6, pi over 4, pi over 3, pi over 2. And we'll throw in some of the quadrantals as well. And this is when I start focusing on radian measures. So at this point, you need to equate pi over 6 as 30 degrees. Pi over 4 as 45 degrees. Pi over 3 is 60. So I am going to be switching to predominantly radian measure. So you do need to keep those in mind, that when I say pi over 6, pi over 4, and pi over 3, I'm referring to 30, 45, and 60 respectively. And then pi is 180 degrees. 3 pi over 2 is 270, and then 2 pi versus 360. And so additionally, with this conversion, also also identifies basically a versatility that I will provide you all. You do not, so no longer moving forward, you have to derive sine of pi over 6, sine of pi over 4, sine or cosine in general of any of the special angles. So what you may notice, there's a few decimals you will have to remember. Sine of pi over 4, if you were to put this in the calculator, well, you'd have to have your calculator in radian measure, which I don't think I really described that yet. So instead, pi over 4 is 45 degrees. So if you put sine of 45 degrees in your calculator, you'll get roughly 0.707 blah, blah, blah. And what that corresponds to is square root of 2 over 2. That is a decimal that you should be familiar with from now on, because I'm no longer making you derive these things, at least for the special angles. So that means if you use your calculator, see square root of 2 over 2, which is 0.707. If you see that number, that is a significant number. And then additionally, sine of pi over 3, which is the same thing as sine of 60 degrees. 0.866, blah, blah, blah. That's another decimal you need to be familiar with. That corresponds to the square root of 3 over 2. And that's really the two main ones. Of course, sine of pi over 6 is 1/2. So that one's not really anything intricate. It's just 0.5. So with all of these being said, sine of 0 is 0. Sine of pi over 6 is 0.5 or 1/2. Just put 1/2. Sine of pi over 4 is square root of 2 over 2. Which is approximate to 0.707. Pi over 3. This one is square root of 3 over 2, which is approximate to 0.866. Sine of pi over 2 is 1. So what we're doing is we're finding some points to plot on the graph to get an idea of what sine looks like. So it says when we plug in 0, we get 0. So if anything, we get that point right in the center. We plug in pi over 6, we seem to get 0.5. So consider that about halfway. So about halfway. And if we plug in the other two, that would be pi over 4 and pi over 3. Then it gets closer and closer, so eventually it peaks at 1. So that's what these values tell us. And so we can move further to consider sine of pi, which is 0, which means that from that top point, we somehow have to get down here. But by symmetry of sign, we know that it's going to arc down due to the natural symmetry of the sine function. Sine is positive and continuous. So if anything, we can start to see this arc. And we can further go on to consider sine of 3 pi over 2, which is -1, and sine of 2 pi, which is 0. So the shape of sine continues in that same arc-like motion. But sine does go on forever in both directions. What we have drawn is one period, as it's called. It will repeat in this pattern in both directions forever. So in other words, if we were to find more points, we would get more points as such. It continues onwards. This. It goes onwards like this. So it goes on forever. Just like this. And you might have seen signs like, or you might have seen oscillations like this, namely with pulses. You might see in the movies or something, the pulse goes up and down every time there's a heartbeat, and then it flatlines and all that stuff. So these pulses are examples of oscillations. Also, audio waves tend to work and they tend to work as oscillations. So these graphs are very important, these graphs. So this is the sine function. I guess another thing to emphasize, this would be good to show everyone how to switch your calculator from degrees to radian mode. To make some of these computations I did over here a little bit more understandable. So I'll come back to the screen. So the issue is, hopefully everybody can see this. So if we tried to do sine of 3 pi over 2 as is, well, that doesn't look right. We're supposed to get -1. Or, yeah, we're supposed to get -1. I did not get -1, so what's the problem? The problem is the calculator is in degree mode, and you can see it. If you have a TI 80 whatever, I might have to get someone else's calculator and show you all, but if you have one of these calculators, then, well, here's the initial problem. It's in degree mode, and you can see a DEG down here. So you'd have to press the DRG button right here. Just means degree. And then you simply just go over to radian mode. It's as simple as that. Press enter. Try that again. You get -1. That's radian mode for this calculator. So that means you can do sine of, let's see, what's one of the ones I did, pi over 4. So now sine of pi over 4 is the 0.707. And I told you that's a decimal you need to know now. That corresponds to the square root of 2 over 2. So let me snag your calculator. So yours is actually already in radian mode.
I just put it in.
Oh, okay. I'm going to put it to degree just for the sake of argument, or whatever, demonstration. So if you have one of the TI calculators, so let's see, same circumstance. If you try doing sine of 3 pi over 2, you get this weird decimal because it's in degree mode, not radian. So you would click mode right here. And you could see radian right here. Just press enter on it. So now radian selected. And if we try that again, it's -1. So just for anyone who didn't know that, if everyone knew that, then I'm just wasting oxygen, I'm sorry. But that's, I figured I might as well show that. So, all right, cool. So showed everyone that. So that's how you can determine all those values in the chart here. And it'll help us actually for doing the same thing, but replacing sine with cosine. So we're gonna go to cosine now. And it's the same idea. We're gonna go ahead and we're gonna compare this to cosine. So we'll go to the same exact values, 0, pi over 6, pi over 4, pi over 3, 2, pi, 3 pi over 2, and 2 pi. And so really we're just plugging each one of those values into the calculator. So now that you know how to put in radian measure, or put your calculator into radian mode, you type in cosine of 0, you get +1. So cool. So cosine of pi over 6, I get 0.866. That's a decimal you need to know now. It corresponds to the square root of 3 over 2. Pi over 4, it gives you another decimal you need to know. That's square root of 2 over 2. Pi over 3, that one's easy. That one's just a half. Pi over 2 is 0. So let's go ahead and plot some of these. So it says, when you plug in 0 for x, you get 1 for y. And then what I'm doing is I'm putting in these 3 intermediate points here. They're just pi over 6, pi over 4, and pi over 3. It says we're slowly decreasing. So 0.866, 0.707, and 0.5. And then at pi over 2, we hit 0. So my graph doesn't really do it justice, but this is supposed to be an arc. This is supposed to be an arc. So this point should be reflective in that regard. And then if we plug in pi, cosine of pi, that is, you would get -1. So when you plug in pi, you get -1 down here. You plug in 3 pi over 2, you get 0. If you plug in 2 pi, you just get 1. 0 and 1. So we can go ahead and also connect these dots using similar logic as before. So not very good on the left-hand side, but that's fine. So notice it's very close. It's very, very close to sine. In fact, perhaps the more astute observer may realize that since sine and cosine are co-functions, one is simply the other one shifted by 90 degrees or pi over 2. So they really are the same shape. It's just one is shifted over pi over 2 radians. So if you took one of these graphs and then just shifted it over by pi over 2 radians, you would get the other graph exactly. But they are different. One starts at the origin and the other one starts at +1. And this is a distinction that you will need to keep in mind. Now you won't have to derive it like this every time. This is just, we're just deriving what the shape looks like. And now that you know the shapes, you can use the shapes accordingly. But it wouldn't be that easy if it's just sine and cosine, bam, next section. Because what about if we want to modify these functions? So let's go ahead and scroll down to something called, well, we're gonna talk about the period, which is the repeating part of the graph. So because the graph repeats on and on forever, the period refers to what's the length of the unique part. So if we were to look up here and figure out, okay, if we can determine what size of this we can isolate to figure out the repeating part, what would that be? So if we go up to the sine example here. So would this be the repeating part in red? Obviously no, because that shape would have to continue on and on and on. Would this be the repeating part? No, it would not, because that means you would just have upward arcs every time. The repeating part is exactly this right here that I have in red. Because you could copy that image, paste it over to the left or the right, and that would stay true to the graph of sine. So what is the length of that segment that I just drew in red? Furthest to the left is 0, the furthest to the right is 2 pi. So the period is 2 pi. So the period of sine of x, 2 pi. Sometimes it's denoted as capital T. If I accidentally use that notation, then that's what it means. Why is it T? I'm not too sure. So that is the period of sine. That is the length of the segment required, such that if you take any part of the sine wave and you find a 2 pi sized interval, you can copy that to the left or right and it would still continue the pattern of sine. So it's a way of looking at knowing what the whole graph looks like by just seeing the one unique part, because everything else repeats, so it doesn't matter. So what about cosine? What is the period of cosine then? So, would this be the period of cosine? No, because it means that that singular arc would have to just keep repeating over and over. You might have already noticed, this isn't it, that is not it, this is it. That is the period of cosine, because with this shape, this sort of valley-like shape, you copy that. In fact, look directly to the left of it. It's the same shape again. And if you were to shift the view of the graph over to the right, you would see exactly that shape again, repeated again and again and again forever. So what is this length? Here's 0 and here's 2 pi. Oh, well, it's 2 pi again. So the period of the graph, well, naturally it's 2 pi. So that's less memorization you have to do, because now you know that the period of both sine and cosine is 2 pi. So again, you won't have to derive this in any rigorous sense like we're doing. This is mainly interpretive in that regard. Just trying to explain what all these things are and how we derive them. But once you have these tools, then we'll see in the following examples how to appropriately apply them. Another bit of terminology as well is something called the amplitude. So the amplitude is the number in front of the trig function. So with this function right here, it's saying, what about if you take a sine function and you multiply it by 3? Or if you take a cosine function and you multiply it by -5, what happens? Well, what happens is you change the amplitude. And in particular, the amplitude refers to, really it refers to the difference. The definition is a little bit technical, but really the amplitude affects your highest point and your lowest point. So for both sine and cosine, the number that you multiply to them is by default 1. And notice there's ones here. That makes sense. But there is a relation between that. And if we change the amplitude, then we're going to be changing those numbers, as we'll see momentarily. So that's quite a bit of information already. It's the period and the amplitude, as well as the graph of sine and cosine. And now for these next example problems, we're really going to wrap all these ideas together to show how we graph modifications to these trig functions. So let's go down to example 4 here. We're going to be graphing y is equal to 3 sine of x over a 1 period interval. Now, a 1 period interval, we only request 1 period because, well, 1 period gives us all the unique information. Once we have 1 period written down, then all the other information is going to be copies of that. So it wouldn't make any sense to continue in that regard. So this is the way so this is how your brains start to come into play now. So generally the process starts off like this. You identify the amplitude. So identifying the amplitude is the number that multiplies the trig function. What number is doing that? It's the 3. So guess what? So technically, I should be careful here. We'll see this in the next problem. I guess just to make this explicit, technically the amplitude is the absolute value of the number, which doesn't change anything here. It'll be a little bit different in example 5 though, straight ahead. But 3, what this tells us is what the top number is going to look like. And by making that negative, it tells us what the bottom number is going to look like. That's how the amplitude affects things. So if anything, we have that down. The next thing we identify is the period. Well, so what's the period of sine? We said above that this is 2 pi. So we're just kind of stealing that information from earlier. After the period, well, to figure out how to graph this thing, we have these particular pieces, as I like to call them. These pieces are going to help us determine what numbers to put as our intervals, because notice there's a bunch of blanks here. We're going to fill in these numbers. To fill them in, we need to know what the increment size is. So what's the difference between these two? What's the difference between these two, and these two, and these two? That's what the pieces component is going to specify. So the pieces, what you do is you drop the period straight down, and you're going to multiply that by 1/4, or in other words, divide this by 4. So this is going to tell us the increment size. So really, this is just pi/2. Because we know how to treat fractions that have pi involved in them. You simplify the numbers and you leave the pi alone. You just throw the pi in at the very end.
Is 1/4 always true?
Yes.
That's a set number?
That's a fixed number.
Okay.
So fixed for sine and cosine. It'll be different for tangent and cotangent, but we'll get to that. So you just always multiply. So that's how you figure out the pieces. You drop the period straight down, and you multiply that by 1/4 every time. That does not change. So from here, the last thing we have to do is figure out the intervals themselves. And so the intervals, we're going to start at 0. And we know what the step size is. We know what the pieces are. So we have to keep adding the piece value. So we're going to add it to 0 to get pi/2. So slowly what we're doing is we're figuring out the intervals here. And then how do we get to the next one? We have to add another pi/2. Just be pi. Because we know that this displacement has to be pi/2. And then the next one, we have to add another pi/2. It would be 3 pi/2. And then we have to do one more. So this would be 3 pi/2, and then you add another pi/2 to get, not that, 2 pi. So that tells us the intervals. And for adding these together, if you try doing this in the calculator with the pi is going to throw everything off. You're going to keep getting decimals. So really what you have to do is, so instead of 0 plus pi/2, what you're really looking at is 0 plus 1/2, and then you throw the pi in at the very end. And then pi/2 plus pi/2, really you're just looking at 1/2 plus 1/2, and then you're throwing the pi in at the very end. So that's how I'm able to figure these out fairly quickly, is I'm treating them as fractions. I'm just taking out the pi, adding the fractions, and then throwing pi at the very end. Notice these are exact values. If you give me approximated answers, I'm going to mark it wrong on a homework or a test. That's cheating. Don't do that. I want exact answers for these intervals. So these have to be exact answers. or else that ruins part of the reason for having you derive everything. And of course, pi plus pi over 2, that is 1 plus 1 over 2, and then you throw pi in at the very end. So that's 3 over 2, and then you throw pi back in. So that's how I'm getting all these numbers. So putting it in the calculator is misleading, and it will not give you exact answers unless you have a really good calculator. But in any case, go ahead and, so this is kind of scratch work off to the side. I'll leave that for now. So that's where those numbers are coming from. And now that we have the 5 interval values, so we have 5 interval values, this will help us with a 1 period interval. So notice I'm gonna scroll up here right fast. This makes sense because we had 1, 2, 3, 4, 5 points to resemble our 1 period. So it makes sense that we need 5 points to represent the period in this case. So that's why we have these 5 down here. In this problem, they're the exact same. And now we need to focus on what does sine of x do? So now we need to go back. So great, gotta go scroll back up again. What does sine of x do? Sine of x has a point. In fact, I'll do this in black. Sine of x has a point here, and then it goes up. It goes back to the x-axis. It goes down, and it goes back to the x-axis. This is going to be a process that we use throughout these problems. So that those 5 points, what you have to remember is that orientation of those points. So how that translates here is a point here, point up here, point here, point down here, and a point up at the x-axis. So just at this point, it just looks like these discretized points that go in this seemingly zigzag manner. But we know that since this is sine, these are actually arcs. And this would be the 1 period interval for 3 sine of x. This is definitely new in comparison to the other stuff, but there is a pattern to it. And hopefully you get fairly acclimated to it rather quickly, as we'll do some similar problems afterwards. Are there any questions so far? If not, the next one is kind of similar, so. If not, then let's look at the next problem. So next one, it replaces 3 sine of x with -2 cosine of x. So, oh good, it's raining outside.
Yes.
I'm glad I rode my bike here.
Right.
That's going to be interesting to figure out. I'll be at the office a while then. Okay, cool. So example 5. So we're going to go through everything again. We're going to start off with the amplitude. So the amplitude looks at the number multiplying the trig function. That's -2. But we have to figure out the absolute value of -2. So amplitude is a positive number. So instead of -2, we simply state it's +2, because we have to find the positive value. So here, that tells us how to mark the increments or the values on the y-axis. Or of course, the positive one goes on top, negative one goes on the bottom. Just how Cartesian planes work. All right, so what was the next thing we did? We looked at the period. What's the period of cosine? Yeah, that's just 2 pi. Okay, next thing we did, we looked at the pieces. So what the pieces say, take your period, multiply by 1/4. That's a fixed value. Just multiply by 1/4. You're splitting up the whole period into quarters. That's what you're doing. And so we get a familiar number. It's pi/2 again. So naturally, the intervals are going to be the exact same. So you need 5 of them. You need 5 intervals, because that gives you 4 spaces in between each one of them. That's 1, that's 2, that's 3, and that's 4. That's the 4 pieces. That's why you need 5 of them. So you always, well, yeah, we're going to start at 0. That's just a standard thing. And we're going to keep going. So 0, but we add the pi/2 increment. And then we add the pi/2 increment to this to get pi. And then pi plus pi/2 is 3 pi/2. And 3 pi/2 plus another pi/2 is 2 pi. So if you want to be technical, this is delta. It's delta. But you don't have to think about that. Why did I say that? That's delta. So if anything, that tells us how to label everything. That tells us exactly how to label the 5 intervals. So there's one thing, though, that I didn't address before that I'm going to address now. It is going to flip. There is a reflection. There's a reflection because of that guy right there. There's a negative sign in front of this whole stinking function. So what that tells us is whenever you see that negative sign, there's a reflection about the x-axis. So that means everything that we would put, we're going to flip it about the x-axis. And I'll explain what that means in a bit. So let's pretend like we didn't even see the reflection part. Let's just ignore that part for now. If we were just graphing cosine, let's go up and see what cosine does. Cosine has 5 points that starts at the top, not the middle, starts at the top, and then goes to the x-axis and goes down, comes back up, levels off at the top. It's this valley-like shape. And so we're going to utilize that exactly by plotting those 5 points. So I'm going to do this in a different color because we're going to ignore this for now. Let's pretend like the reflection didn't exist. Then you would put a red there, and here, down here, and up here, and up here. We are copying the dots from the cosine function. So this is what you would do if we did not have a reflection. Since we have a reflection, each one of those dots is going to flip about the x-axis. So the true, I'm I'm going to put this in black now. So the point up top now reflects down here. And the point in the middle really doesn't change because it's on the x-axis. And that red point at the bottom here now comes to the top. Point on the x-axis stays, and that point up at the top goes down here at the bottom. So that's how the reflection changes things. So this is the true orientation of the points. And now we can combine them together. So instead of this valley-like shape or this perhaps cup-like shape, it's simply flipped upside down. That's what the reflection means. It's just this upward cup-facing thing is now flipped upside down. And that would be the graph. Hopefully this is becoming a little bit more familiar. Still a little shaky, I'd imagine, but we will see this very repetitious process throughout these problems. And hopefully the goal is to make this boring. That sounds fair. Make this a fairly boring and fairly ubiquitous process. So, any questions? Because if not, I'm going to throw in a new element to all of this. So, what is this new element, you might ask? The new element is, well, we've talked about when numbers multiply the trig function. But what about if a number multiplies x directly? What happens then? Not the whole trig function, but the x value directly. What happens? And really what happens is that, well, really this is changing the frequency of the graph. In other words, the period of the graph will now change. This is more crucial of a point than its small text implies. By multiplying a number to the x variable directly, you are changing the period of the graph. That means that it will oscillate more quickly or more slowly, depending on the number. And we're going to see how that affects things in example 6 here. So the function we are looking at, cosine of 3x. So notice there is a 3 multiplying the x value, not the whole trig function. So that 3 does not affect the amplitude. So by starting off with the amplitude is just 1. That's the number that multiplies the whole trig function, but there's no number there. So it's understood to be 1. So we know what numbers to put here and here, if any. From here, we can go ahead and determine the period. Now before, we would say that the period is just 2 pi. We can go ahead and jot down 2 pi, but that's not the complete picture, because now there is a number multiplying the x directly. Whatever that number is, it turns out to be 3 in this case, that is what we divide the period by. And yes, it's division, not multiplication, it's division. So that's why there's a 3 right here. It comes from that 3 multiplying to the x directly. So that is how multiplying the x directly will change the period. So what about the pieces? Does it change the pieces at all? Well, not really, because you still drop down what the period is, and you're going to multiply that by 1/4. So still 1/4. That doesn't change. So 2π/3 times 1/4 seems to be π/6. Again, really what you're looking at is 2/3 times 1/4. So that's 1, that's a 2, and then that's 1/6. And then you throw the pi back in. So the pieces are π/6. So now this tells us the increment size. So if we go to determine our intervals again, we're not going by intervals of π/2 anymore. We're starting at 0. We're going to add to 0 π/6. So 0 plus π/6, that one's obvious, that one's π/6. What's π/6 plus π/6? That's 1/6 plus 1/6 with the pi thrown back in. That would be 2π/6, which simplifies.
π/3.
Yeah, that's π/3. So that's where I'm getting these numbers from. That's π/3. And then we add to π/3, or 1/3, another 1/6, and then throw the pi back in at the end. So 1/3 plus 1/6, you end up getting 3/6, so 3π/6, but that's just π/2. And then we have one more. So π/2, which we'll look at 1/2, plus another 1/6. That's 4π/6, which that is just 2π/3. So that's how we determine the new interval values. So that's how it affects the period, and thus the intervals. Here, the final step we have to do is figure out what the graph of cosine does so we know where to put the 5 dots at. Because we have a cosine function, that's what we started off with. So the cosine function will tell us where we put the dots. So let's scroll up. So cosine. So which one was cosine? Cosine was the valley looking one. So again, it tells us that the 5 dots starts off at top, hits the x-axis, goes down, comes back up, and levels off as such. So cosine tells us we start off at the top, come down to hit the x-axis, and then we go down to -1, we come back up, and we level off at 1. This tells us exactly the template that we will now fill in the arcs for. Like that. And that would be the graph of cosine of 3x. So any questions, or do you want me to just go ahead and do example 7? because it's pretty similar as well. It's 5-1 in the textbook. That is a good question. Yeah, we could. Vince, you're normally the one who reminds me of this, so it's your fault.
I didn't even think about it this time.
Yeah, I
I figured
didn't.
we were back on track.
Yeah, I completely forgot. This is 4-1 in the book. This is 4-1. So we're doing everything in chapter 4 right now, in the book. So let me go back and write that. That's a good question. So this is 100%. Well, maybe I shouldn't exit it out, because I like my notes, but this is 4.1 in the book.
Good thing it is 100%. Just imagine half of it's coming from 4-1, the other half's gonna come from 5-8, you know?
Yeah, let me just assign some stuff from chapter 8. Why not? Oh yeah, because if you try doing stuff in 5.1, you might not have too much fun. Fundamental identities, yeah, that's not a very fun section for some people. It's more so proofs, which are, I think they're fun, but a little biased. So yeah, definitely 4.1 in the book. 100% 4.1 in the book. All right, cool. Let's go back down. So let's go ahead and do example 7 here. So it's another problem. We're going to go ahead and go through the same exact process. Start off with finding the amplitude. Maybe I'll make this more of a participation aspect. Blake, what's the amplitude? It is 1. So the number that multiplies the trig function will tell you the amplitude, but we have to take the positive value of it. So you would think, oh, it's -1, but you have to take its absolute value. So it's just 1. So there's a 1 up here, -1 down here. What about the period? What's the period change?
2 pi over 4.
Yeah, it's 2 pi over 4. So remember, when a number multiplies the x directly, that is going to change the period. So now we just divide by 4. But we can actually simplify that. Maybe I should erase this a little bit. Yeah, 2 pi over 4 is just pi over 2. I'll just put that down. Pi over 2. Erase that and correlate it here. Cool. So the period's pi over 2. So that tells us the size of the increments. All right, we move on to the pieces. Does anyone happen to already know what the pieces, what value that is?
I agree.
Yeah, it is pi over 8. So let's derive that. Drop the pi over 2 down. So drop that down. Multiply that by 1 over 4. Simply just pi over 8. And so the intervals, we need 5. We start off with 0. And we're just going to keep adding pi over 8. It's just in another sense, it's just increments of 1 over 8. And that's really all it is. So pi over 8, and then pi over 8 plus pi over 8 is pi over 4. And that's 3 pi over 8. And that's pi over 2. So hopefully everyone is starting to see where these numbers are coming from. It's 0, it's technically 0, 1 over 8, 2 over 8, 3 over 8, 4 over 8. Because it's increments, but I simplified the fractions.
And the last was always going to be the period.
that's until we start introducing horizontal shifting.
Yeah.
But yeah, so for now, the last one is always the period.
Or minus, depending.
I mean, the period's always going to be the last interval minus the first interval value. So that's always true. Just we keep hitting 0 for the first one because we're not shifting left or right any. We're going to talk about that next time, though. So, well, if anything, we can go ahead and start filling in 0, pi over 8. And then what was 2 pi over 8, we simplify to pi over 4. 3 pi over 8, and then 4 pi over 8, which simplifies to pi over 2. And there's a reflection. There's a reflection about the x-axis, which means every point we plot for an original sine function, we would have to flip it about the x-axis. So what does the sine function do? Let's look up one more time. To the very top. Sine function starts off in the middle, goes up and back down, and then it goes back up again. So that tells us the kind of zigzag that we need to plot out with these discrete points, which I'll do down here. Actually, I'll do this in red because I'm going to change these. This is what it would be if it were just regular sine without a reflection. So if there was no reflection, this is what you would do. And then you would just connect all the dots. There is a reflection, though, so well, obviously anything on the x-axis is going to stay the same. And then anything not on the x-axis flips. Oops. So really, it's these points in black that I care about. So it's the sine function, but it's flipped about the x-axis. I'm making pretty good timing. I like this. All right, cool. I feel like for example 8. So example 8's a little hardcore. So I want you all to try it. So I can drink some tea. You all try example 8. Okay, I'll go ahead and just start filling in the pieces here. Okay, so amplitude, yeah, it's 3. So it's the number that multiplies the trig function as a whole, but we have to make it positive. So amplitude is 3. So if anything, that tells us top y value, bottom y value. Hopefully, one's got up to here. What about the period? This one should be kind of interesting. See how you all did it here.
4 pi.
It is 4 pi. So the reason why it's 4 pi, for those of you following along, it's 2 pi divided by 1/2. So it's 2 pi divided by 1/2. Yeah, it's 2 pi times 2. So it's 4 pi for the period. So the pieces, well, the pieces actually work out pretty nicely.
4 times 3, which is pi. Or times 3, which is pi.
Yes, so it's 4 pi times 1/4, which is just pi. So that's a really easy increment to go by. Just increments of 1. Yeah, just increments. So it starts off a little bit wonky, but so it's start off at 0, you add pi to it, and then you keep adding pi to it. 2 pi, 3 pi, we need one more, 4 pi, which tells us 0, pi, 2 pi, 3 pi, 4 pi.
And then there's a reflection.
And there's a reflection. Great, there's a reflection. So. We generally don't worry about reflections over the y-axis in this class, so it's always just going to be the x-axis, if there is one.
And for it to be over the y-axis, it would have to be like negative 1/2 x, right?
Yeah, negative 1/2 x. You can always try to get out of it using even odd properties, but we haven't talked about those yet. So reflection about the x-axis, we have all the information we need to go ahead and plot this. So cosine, let's see how good your memories are. So I'm going to plot it without the reflection first, so I'll do that in red. Cosine without the reflection would start up here, go down, up, up. That would be without the reflection. But with the reflection, that top point reflects down here, middle point stays the same, go up here, middle point here. So I'm going to erase those. And we can go ahead and fill in final details. And that is the graph. Good timing. That concludes the section. I guess that means I have to assign this section and make it due Tuesday. So I will do that. So it's, is it 4 or 5 problems? They're all pretty much like this. So yeah, that's pretty much it. This homework is due next Tuesday. I'll have everything graded for next Tuesday as well, by next Tuesday. So other than that, that's all I have. I'll get too soaked outside for those of you here. Virtual people, you don't have to worry about that. And yeah, have a good day.